perform a minimum fault current calculation for a 30-cycle period using the impedance method, we will follow a structured approach. Firstly, we need to gather the necessary system data. This includes the system voltage in kilovolts, the base megavolt amps, transformer impedances as a percentage on the base megavolt amps, line impedances in ohms, and generator impedances, either in per unit or in ohms. Secondly, we will calculate the equivalent system impedance. This involves several steps. 1. Convert the transformer impedances to per unit on the system base megavolt amps. 2. Convert the line impedances to per unit on the system base megavolt amps. 3. Convert the generator impedances to per unit on the system base megavolt amps. 4. Sum all the per unit impedances in series from the fault location back to the system source. Thirdly, determine the fault current using the provided formula. The fault current is equal to the base voltage divided by the equivalent reactance multiplied by 30. The base voltage is the system voltage in kilovolts multiplied by the square root of 3 and scaled to the base megavolt amps. The equivalent reactance is the equivalent system impedance in per unit. The number 30 represents the number of cycles for which the fault current is being calculated. Fourthly, adjust for reactance. Use the IEEE Red Book reactance table to determine the multiplier factor, designated as F for the system voltage and frequency. The adjusted fault current is then calculated by multiplying the initial fault current by this factor F. Several important notes must be considered. The 30-cycle time interval is used because it represents the typical time for protective relays to operate and isolate the fault. Also, a calculated fault current is the minimum fault current expected, assuming no contribution from induction motors or other loads. Let's work through an example. Suppose we have the following system data. The system voltage is 13.8 kilovolts. The base megavolt amps is 100. The transformer impedance is 5% on 100 megavolt amps. The line impedance is 0.1 ohms and the generator impedance is 10% on 100 megavolt amps. Now let's proceed with the calculations. Firstly, the transformer impedance in per unit is 5% divided by 100%, which equals 0.5 per unit. Secondly, the line impedance in per unit is 0.1 ohms divided by the quantity of 13.8 kilovolts multiplied by the square root of 3, then divided by 100 megavolt amps. This equals 0.1 per unit. Thirdly, the generator impedance in per unit is 10% divided by 100%, which equals 0.1 per unit. Fourthly, the equivalent impedance is the sum of these per unit impedances. That is 0.5 per unit plus 0.1 per unit plus 0.1 per unit, which equals 0.1501 per unit. Fifthly, the fault current is calculated as 13.8 kilovolts multiplied by the square root of 3, then divided by the quantity of 0.1501 per unit multiplied by 30. This results in a fault current of 7.46 kiloamps. Sixthly, we refer to the IEEE Red Book multiplier. For 13.8 kilovolts and 60 Hz, this multiplier is typically 1.5. Seventhly, the adjusted fault current is calculated as 7.46 kiloamps multiplied by 1.5, which equals 7.83 kiloamps. Therefore, the minimum 30-cycle fault current for the system is 7.83 kiloamps. This comprehensive calculation provides a solid understanding of how to determine the minimum fault current in a system, which is crucial for designing effective protection schemes and ensuring electrical safety. Firstly, to elaborate further on gathering system data, it's essential to ensure accuracy and completeness. The system voltage should be the nominal voltage at the point of fault calculation. The base megavolt amp should be a convenient value, often 100 megavolt amps, for normalizing impedances. Transformer impedances are typically provided on the transformer nameplate and should be converted to the system base. Line impedances can be obtained from utility data or calculated based on conductor size and spacing. Generator impedances are usually provided by the generator manufacturer. Secondly, the conversion of impedances to a per unit basis is a critical step. Per unit values simplify calculations and allow for easy comparison of impedances across different voltage levels. The formula for converting impedance from ohms to per unit is Z per unit equals Z ohms multiplied by the base megavolt amps divided by the base kilovolts squared. Ensure that all impedances are converted to the same base megavolt amps. Thirdly, when summing the per unit impedances, it's important to consider the network topology. Impedances in series are simply added, while impedances in parallel require the use of the parallel impedance formula. Pay close attention to the connections of transformers and generators to ensure that the impedances are correctly combined. Fourthly, the fault current calculation formula is based on Ohm's law and assumes a bolted three-phase fault. In reality, fault currents may be low due to fault impedance or arc resistance. However, the calculated value provides a conservative estimate for protection coordination. Fifthly, the IEEE Red Book multiplier is used to account for the X to R ratio of the system impedance. The multiplier is typically close to 1.0, but can be significant for systems with high X to R ratios. Consult the IEEE Red Book for the appropriate multiplier value for the system voltage and frequency. Sixthly, the adjusted fault current represents the expected fault current after accounting for the system reactant. This value is used for selecting protective devices and coordinating relay settings. Seventhly, it's important to consider the limitations of the minimum fault current calculation. The calculation assumes no contribution from induction motors or other loads. In reality, these contributions can significantly increase the fault current, particularly during the initial cycles of the fault. For a more accurate assessment, a full fault study should be performed using specialized software. Furthermore, the 30-cycle time interval is a typical value, but may not be appropriate for all systems. Some protective relays may operate faster or slower than 30 cycles. The appropriate time interval should be based on the specific relay characteristics and system requirements. In addition to the above steps, it is important to document all assumptions and calculations. This documentation will be helpful for future reference and troubleshooting. The minimum fault current calculation is a fundamental tool for electrical engineers involved in power system design and protection. By following the steps outlined above and understanding the underlying principles, engineers can ensure the safety and reliability of electrical systems. To provide a more comprehensive understanding, let's consider a more complex example. Assume we have a system with the following components: a generator with a rating of 50 megavolt amps and an impedance of 12% on its own base, a step-up transformer with a rating of 75 megavolt amps and an impedance of 8% on its own base, a transmission line with a length of 100 kilometers and an impedance of 0.5 ohms per kilometer, a step-down transformer with a rating of 100 megavolt amps and an impedance of 6% on its own base, a distribution feeder with an impedance of 0.2 ohms. The system voltage at the point of fault is 13.8 kilovolts and the base megavolt amps is 100. Firstly, we need to convert all impedances to the system base of 100 megavolt amps. The generator impedance becomes 0.12 multiplied by 100 divided by 50, which equals 0.24 per unit. The step-up transformer impedance becomes 0.8 multiplied by 100 divided by 75, which equals 0.1067 per unit. The transmission line impedance is 100 kilometers multiplied by 0.5 ohms per kilometer, which equals 50 ohms. This must be converted to per unit using the formula Z per unit equals Z ohms multiplied by the base megavolt amps divided by the base kilovolt squared. That is 50 ohms multiplied by 100 megavolt amps divided by 13.8 kilovolts squared, which equals 0.2628 per unit. This step-down transformer impedance becomes 0.6 multiplied by 100 divided by 100, which equals 0.6 per unit. The distribution feeder impedance is 0.2 ohms. This must be converted to per unit using the same formula as the transmission line impedance. That is 0.2 ohms multiplied by 100 megavolt amps divided by 13.8 kilovolts squared, which equals 0.105 per unit. Secondly, we sum all the per unit impedances in series from the fault location back to the generator. The total equivalent impedance is 0.24 per unit plus 0.1067 per unit plus 0.2628 per unit plus 0.6 per unit plus 0.105 per unit, which equals 0.67055 per unit. Thirdly, we calculate the fault current using the formula fault equals V base divided by X equivalent multiplied by 30. The base voltage is 13.8 kilovolts multiplied by the square root of 3, which equals 23.89 kilovolts. The fault current is 23.89 kilovolts divided by 0.67055 per unit multiplied by 30, which equals 1.188 kiloamps. Fourthly, we adjust for reactance using the IEEE Red Book multiplier. Assuming a multiplier of 1.5, the adjusted fault current becomes 188 kiloamps multiplied by 1.5, which equals 1.247 kiloamps. Therefore, the minimum 30 cycle fault current for this system is 1.247 kiloamps. This more complex example demonstrates the application of the impedance method to a system with multiple components and different voltage levels. It also highlights the importance of accurately converting impedances to a common base and considering the network topology. In addition to the per unit method, there are other methods for calculating fault currents, such as the ohms method and the computer-based method. The ohms method involves calculating the actual impedance in ohms for each component and then summing the impedances in series or parallel. This method can be more tedious than the per unit method, but it may be useful for small systems or for verifying the results of the per unit method. The computer-based method involves using specialized software to model the power system and calculate fault currents. This method is the most accurate and efficient for large and complex systems. The software can automatically handle the conversion of impedances, the network topology, and the effects of induction motors and other loads. Regardless of the method used, it is important to understand the assumptions and limitations of the calculation. The calculated fault current is an estimate and may not be exactly equal to the actual fault current in the system. However, the calculation provides a valuable tool for designing and coordinating protection systems. The importance of protective devices cannot be overstated. Protective devices like circuit breakers, fuses, and relays are the first line of defense against damage from fault currents. These devices sense the overcurrent and quickly interrupt the circuit, preventing damage to equipment and injury to personnel. The selection and coordination of protective devices is a critical aspect of power system design. The devices must be selected to withstand the maximum fault current and must be coordinated to ensure that the device closest to the fault clears the fault first. This coordination prevents unnecessary outages and minimizes the impact of the fault on the system. Regular maintenance and testing of protective devices is also essential. Protective devices can degrade over time due to environmental factors or mechanical wear. Regular testing ensures that the devices are operating correctly and will function as intended when a fault occurs. In summary, the minimum fault current calculation is a fundamental tool for electrical engineers. By understanding the principles and applying the methods outlined above, engineers can ensure the safety and reliability of electrical systems. Remember to gather accurate system data, convert impedances to a common base, consider the network topology, adjust for reactance, and understand the limitations of the calculation. Additionally, proper selection, coordination, and maintenance of protective devices are critical for preventing damage and ensuring safety. Furthermore, always consult relevant standards and guidelines such as the IEEE Red Book and the National Electrical Code for specific requirements and recommendations. Staying up to date with the latest industry practices is essential for ensuring the safety and reliability of electrical systems. Let's delve deeper into some of the factors that can affect fault current calculations. One important factor is the source impedance. The source impedance is the impedance of the power system upstream of the point of fault. This impedance limits the amount of current that can flow into the fault. The lower the source impedance, the higher the fault current. The source impedance can vary depending on the configuration of the power system and the number of generators or transformers connected to the system. Another factor is the transformer impedance. The transformer impedance limits the amount of current that can flow through the transformer during a fault. The higher the transformer impedance, the lower the fault current. Transformer impedance is typically expressed as a percentage of the transformer's rated volt-amp capacity. Another factor is the cable or conductor impedance. The cable or conductor impedance limits the amount of current that can flow through the cable or conductor during a fault. The impedance of a cable or conductor depends on its size, length, and material. Larger cables and conductors have lower impedance. Longer cables and conductors have higher impedance. Copper conductors have lower impedance than aluminum conductors. Another factor is the motor contribution. Motors can contribute to the fault current during a fault. When a fault occurs, a motor's magnetic field collapses and the motor acts as a generator, feeding current into the fault. The amount of motor contribution depends on the size and type of motor, as well as the system voltage and frequency. Another factor is the arc resistance. The arc resistance is the resistance of the arc that forms at the point of fault. The arc resistance can significantly reduce the fault current, especially for low voltage systems. The arc resistance depends on the voltage, current, and the type of fault. Another factor is the grounding system. The grounding system is the method used to connect the neutral point of the power system to ground. The grounding system can affect the magnitude and duration of the fault current. There are several types of grounding systems, including solidly grounded, resistance grounded, and ungrounded. Each type of grounding system has its own advantages and disadvantages. Solidly grounded systems provide the lowest fault impedance and the highest fault currents. Resistance grounded systems limit the fault current to a predetermined value. Ungrounded systems do not provide a path for fault current to flow, which can make it difficult to detect and clear faults. In addition to these factors, there are other factors that can affect fault current calculations, such as the presence of harmonic currents, the type of fault, and the operating temperature of the equipment. It is important to consider all of these factors when performing fault current calculations to ensure that the results are accurate and reliable. To further illustrate the importance of accurate fault current calculations, consider the following scenario. An electrical engineer is designing a new power system for a commercial building. The engineer performs fault current calculations to determine the appropriate size and rating of the protective devices. However, the engineer makes an error in the calculations and underestimates the fault current. As a result, the protective devices are not able to interrupt the fault current quickly enough. This can lead to a number of problems, including damage to equipment, injury to personnel, and a prolonged power outage. In this scenario, the error in the fault current calculations could have been avoided by carefully reviewing the calculations, using appropriate software, and consulting with experienced engineers. Accurate fault current calculations are essential for ensuring the safety and reliability of electrical systems. To enhance understanding, let's consider specific types of faults. A three-phase fault is a symmetrical fault where all three phases are shorted together. This type of fault typically results in the highest fault current. A single line to ground fault is an unsymmetrical fault where one phase is shorted to ground. This type of fault is more common than a three-phase fault, but typically results in a lower fault current. A line-to-line fault is an unsymmetrical fault where two phases are shorted together. This type of fault results in a fault current that is between the values of a three-phase fault and a single line-to-ground fault. A double line-to-ground fault is an unsymmetrical fault where two phases are shorted to ground. This type of fault is less common than the other types of faults, but can result in high fault currents. The type of fault that occurs can affect the magnitude and duration of the fault current. It is important to consider all types of faults when performing fault current calculations to ensure that the protection system is adequately designed. Let's also address the role of software in fault current analysis. Modern power system analysis software provides powerful tools for calculating fault currents. These software programs can accurately model complex power systems and can automatically perform the necessary calculations. Software can also help to identify potential problems in the power system, such as areas where the fault current is too high or where the protection system is not adequately coordinated. When using software for fault current analysis, it is important to ensure that the software is properly configured and that the input data is accurate. The software should be validated against known results to ensure that it is producing reliable results. The software should also be updated regularly to incorporate the latest standards and guidelines. Software can greatly simplify the process of fault current analysis, but it is important to remember that the software is only a tool. The engineer must still understand the underlying principles of fault current calculations and must be able to interpret the results of the software. In conclusion, performing accurate fault current calculations is a critical aspect of power system design and protection. By understanding the principles, applying the methods, and using the appropriate tools, engineers can ensure the safety and reliability of electrical systems.